Hi there. Today we're going to be continuing on talking about inverses. And I know that the heading here says finding an inverse function. We're going to do that in the next lesson. Today we're going to focus on the first learning target, which is I can determine if a function has an inverse that's also a function. And so I want us to recall a little bit about what a function is. Remember that a function is a relation. A relation is any set of ordered pairs, any input-output values, x's and y's. But a function is special in which each input has only one output. And since our input variable is like x and our output is like y, that means that for each x, there's only one y. So here are tables for a function and its inverse relation are given. What we're going to do is we're going to decide if the inverse is an inverse function or just an inverse relation, okay? So again, what these represent on the left are the original tables, and then these on the right are the inverse tables. So all of these are functions, okay? But we're going to look at the inverse relation to see if, or at the inverse table to see if that is a relation or if it is indeed a function. So if I look here, notice that the x's and y's are switched in all the tables. And I look at this and I see that -1 gives me -2, 1 gives me -1, 3 gives me 0, 5 gives me 1, 7 gives me 2. I can see that each input gives me just one output. So that is an inverse function, okay? And again, that's because each input gives me only one output. That makes it a function, okay? What if I look at example B? If I look at example B, I see that 8 gives me -2, -1 gives me -1, -4 gives me 0. Wait a minute. I see here that -1 gave me -1 and -1 gives me 1. And here 8 gave me -2, but here 8 also gave me +2. That means that this is not a function. It's still an inverse, but it's just an inverse relation. Okay, and the reason is because some inputs give us more than one output. And even if just one input gives us more than one output, it's not a function, but still, okay? And then now let's look at example C. We can see that the x's and y's have switched from the original to the inverse. And I look and I have all of these x's that give unique y's. So this again would be an inverse function. Again, that's because each input gave only one output. So what do we notice? Always, sometimes, never. The inverse of a function is it always, sometimes, or never a function too? Well, here was a case where the inverse was a function. Here was a case where it wasn't. So what that means is that the inverse of a function is sometimes a function too. Sometimes it is, and sometimes it's not. So how could we look, instead of having to make the inverse table, how could we look at a given table of values? And by a given table of values, what I mean like at the original table. So at the original table of values, and decide if its inverse is a function. Well, let's look at this one where the inverse was not a function. Notice that there were x's that were repeated. And if there were x's repeated in the inverse, where would we see those in the original? That's right, we'd see them as the y values. Okay. Similarly here with the -1 and the -1 that were repeated in the x's, here this was repeated in the y's. So what we can do is we need to make sure, in the original table, we need to make sure that none of the y values repeat. Because these would become x's. So these would become repeated x values when we switch the x and the y for the inverse. Okay. So that way we can just look, instead of having to make a different table, we can just look and say, oh, look, here are two y values. That means that if we switch, I'm going to have x values that give different y values, so that won't be a function. Okay? And back in the day in Algebra 1, you may have learned about a test to see that you can do on a graph to see if it is a function. And that is called the vertical line test. The vertical line test is a test that we do on a graph to determine if it is a function. So we do that on a graph to see if it is a function. And a vertical line is always in the form x equals. And so what we do is we want to make sure that if it passes the vertical line test, each x equals line only hits the graph once. Because x equals is our input. So then for each input, every x only hits once each time, okay? So if I were to do the vertical line test on something like a parabola, okay, arrows, notice that if every vertical line, that hits only once. This hits only once. That hits only once. That means that that's a function. But if I had something like this, notice here's a vertical line that hits twice, so that would not be a function, all right? So that's the vertical line test. Hopefully you remember that from Algebra 1. But now let's think about it. How could we look at a graph and determine if its inverse is a function? So let's think about how a function is related to its inverse. Well, to find an inverse, we have to switch the x and y's, right? So we would want our inverse function to pass a vertical line test, which means in the original function, that x would really be a y and would be a horizontal line. So what we can do, we can say since the inverse would need to pass a vertical line test, and vertical line test is when we have x equals something, and the original would need to pass a horizontal line test. So that's y equals. And again, that's because in an inverse, the x and y values switch. Okay. So if the inverse needs a vertical line test, that means the original would need a horizontal line test because your x's and y's switch. So that brings us to this next thing, which is the horizontal line test. The horizontal line test says that the inverse of a function f is also a function if and only if any horizontal line intersects the graph of f only once, okay? So one note about this horizontal line test is a test we do on the original function to decide if the inverse is a function too. Okay? So if we look at this, this is our little graph of f of x that's here. Okay? Here's our graph of f of x. It itself is a function. It passes the vertical line test, okay? But we want to decide if the inverse is a function. So what we're going to do is look at different horizontal lines. Notice that any horizontal line we draw only crosses the graph once. That means that the inverse is a function. But let's look at this guy here. This is a function, this f of x. It itself passes the vertical line test. So f of x is a function. But if we look at if we switch the x and the y's, that means we'd want to test the horizontal line because the x's would become y's and y's would become x's. So notice that this has several horizontal lines that cross more than once. And that means that the inverse is not a function. So this itself is a function, but the horizontal line test again decides if the inverse is a function too. So what we're going to do is graph a couple functions and then determine whether the inverse of f is a function. So let's look at number one, at A. We have f of x equals negative 2x minus 3. Well, this is a nice function to graph. This is a linear function. I know that my y-intercept, I'll just make a little note that this is linear. My y-intercept is 0, negative 3. My slope is negative 2, so I can go down 2 over 1. And again, I love being able to fill the graph. That helps me make a nice straight line. And there is my function. Okay, so that's the function itself. This is a function. Is the inverse a function? What we'll do is we'll think about a horizontal line test. If I think about any horizontal line, it only crosses once. So is the inverse a function? We are going to say yes. And the reason is because f of x passes the horizontal line test. And I'm going to lovingly call that the HLT, okay? So one thing is that I don't want you to say it passes the HLT because we were talking about the inverse. What we're doing is we're looking at the original function, okay? So in our explanation, that f of x is the original function. So the reason we know that the inverse is a function without graphing it is because the original function passes the horizontal line test. Okay? Let's try to graph letter B. F of x equals 3 times the absolute value of x minus 1 plus 2. Well, we know that this is absolute value. That's going to be a V shape. We can look at our vertex. We see here that our vertex is going to be positive 1, 2. And the opening is going to have a slope of plus or minus 3. And since it's positive, we're going to go up. So we're going to go up 3 over 1 in both of those directions here. Okay. And then we can decide by using the horizontal line test, like this itself is a function, okay? This is our f of x, a function. Will the inverse be a function? Will we do the horizontal line test? Notice that it crosses 2 times in several places. So we're going to say no, the inverse is not a function. And it's because f of x does not pass the horizontal line test. Okay. So then what if we have x cubed plus 1? Well, this is a cubic function. I might not know what we know what the end behavior is going to be, right? We know that because this is an odd degree that it's going to end, and positive leading coefficient, it's going to end up on the right and down on the left. But maybe I don't know some of the points. So maybe I could just think about like a little table to help. Again, when in doubt, we can always do a little table and use values like -2, -1, 0, 1, and 2. And this isn't much to substitute. -2 cubed is 8, plus 1 is -7. -2 cubed is -8, plus 1 is -7. -1 cubed is -1, plus 1 is 0. 0 cubed is 0, plus 1 is 1. 1 cubed is 1, plus 1 is 2. 2 cubed is 8, plus 1 is 9. So I can have -2, 1, 2, 3, 4, 5, 6, 7, -7, -1, 0, 0, 1, 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, we get this idea, okay? And that's what this is going to look like. So let's do the horizontal line test on this original function to see what's going on. So if I look, notice that each horizontal line only crosses once. So is the inverse a function? I'm going to say yes. And why? Because that original function, f of x, passes the horizontal line test. Okay. In my explanations, I'm always talking about the original function. I do not use the word it, okay? There are too many things we're talking about for us to use the word it and for it to make sense, okay? So this is also a nice review of how to graph these different pieces too. It's really cool. All right, so why might we see a domain restriction in the problem? So let's graph the function and let's decide if the inverse of f is a function. And in letter D, we have this f of x equals 2x squared minus 1. So this is a quadratic. And it could be considered in vertex form. It could be considered in standard form because there's no bx term. Let's, for this one, make a little table. And if I were to think about graphing in either vertex or standard form, I see that my, well, we'll do standard form. I see that if I'm using the -b over 2a, that my b value is 0. So it doesn't really matter what a is. I know that the x-coordinate of the vertex is going to be 0. And so I'm going to put that vertex in the middle. And then I'll go around it, 1, 2, -1, -2. And I can substitute 0 in pretty easily, or use the idea that this is vertex form. H is 0, K is -1. I know that 0, -1 is going to be the vertex. So then I want to find 1 and 2, and then because I'm doing that, I can use the symmetry. So f of 1 is 2 times 1 squared minus 1. So that's 2 times 1 minus 1. 2 minus 1 is 1. And then I can find f of 2 as well. 2 times 2 squared minus 1. I'm going to square the 2 first, doing order of operations. Then 2 times 4 is 8, minus 1 is 7. And so then at this point, because our vertex is in the middle, we can use symmetry to find the other points in the table. So I have -2, 7, -1, 1, 0, -1, 1, 1, and 2, 7. And we might see a problem already. Do you notice that in our original table, we have y values that are repeated? So I look at this and I see if I do the horizontal line test on this graph that it does cross more than once. So is the inverse a function? No. And so the reason is that f of x does not pass the horizontal line test. And again, this is a function, okay? But if we switch the x and y, if we deal with the inverse, that inverse would not be a function. Well, I want to look at letter E. Letter E is really similar to letter D, except it has this extra piece in it. And what this is saying is that x, because I know we're pretty weak with inequalities, is greater than or equal to 0. And so what that means is that if I'm going to be making a table of values, this 0 is where I'm going to start. I'm just going to have values like 0, 1, and 2 because I only want x values that are greater than or equal to 0. So if I put 0 in, I get -1. Now this is the same function, guys. So if I put 1 in, once again, I'd get 1. And if I put 2 in, I'd get 7. So if I plot those points, 0, -1, 1, 1, and 2, 7, this is what I have. Now, when I think about putting the arrows on the ends, I start at 0, and I can go greater than 0, but I'm not going to have an arrow on this side. So this is the only part of the graph that we care about. What we're doing here is saying that we're dealing with this function, but this is greater than or equal to 0. So we only care about the part that's greater than or equal to 0. Now, when we consider this function, is this inverse a function? Or sorry, is the inverse of this a function? Well, look at this. What we have is we have this horizontal line test, and it passes the horizontal line test. So yes. And why is that? Because our f of x passes the horizontal line test. So the only difference in D and E was this domain restriction, okay? And so what we can see is that if we just have like a normal quadratic, we're going to have an issue as far as the horizontal line test is concerned, okay? But if we are restricting the domain, that allows its inverse to be a function itself, okay? So sometimes what you'll see is that if you see questions where we have this, like this saying that x can only be these values, it's doing that so that when I find the inverse can be a function too, okay? If we don't see that restriction, then we'll have an issue as far as the inverse goes, okay? And that's what we have for today. Have a great one. Thank you.